I hope you have a very good day today. Today, I'm going to give you a video lecture about the oscillator and clock in embedded system application, particularly 8051 microcontroller. There are so many embedded systems, all embedded systems operate required required a crystal to synchronize its operation. Looking at human biology system, we as a human um, require our heart to generate pulses to circulate the blood around our body, and in order to synchronize our motion or synchronize our movement, hand movement, our walking movement, how we think, and so on. In microcontroller perspective, it is also required an oscillator to generate pulses, a constant pulses, in order for microcontroller to synchronize its operation. Microcontroller operation can be mathematical operation, control operation, and many more. One of the commonly used oscillator circuit is a ceramic oscillator. This is the most lowest cost alternative of oscillator circuit, whereby it consists of the combination of resistor and capacitor circuit. On the other hand, one of the most popular oscillator is crystal oscillator. Ceramic oscillator, even though it is the lowest cost, but it have frequency stability and accuracy issues. Meanwhile, a crystal oscillator overcome these issues. Okay, both of these oscillator generate pulses and generate frequencies. In this case, we call it the clock frequencies. We call it as small letter f. It's establish a smallest interval of time, and pulses we call the pulses as p. Okay, the circuit for oscillator or ceramic oscillator in 8051, the oscillator is connected on pin 18 and 19. Okay, as I mentioned before, the oscillator generate a series of pulses. So the pulses is, we can say that the pulses also can be translated into state machine. Okay, whereby two pulses is equivalent to one state, and one machine cycle is equal to 6 states. So one machine cycle is actually consists of 12 pulses. Assume that we have a crystal oscillator with a value of 11.0592 megahertz. We have seen that 12 pulses is for one cycle. So if 8051 is using crystal oscillator value 11.0592 megahertz, so it is actually generate 11 million 59,200 pulses per second. So how many cycles in 11.0592 megahertz can generate? So we have information that 12 pulses for one cycle. So for oscillator value 11.0592 megahertz. We just divided it by 12. We got 8051 with 11.0592 megahertz crystal can generate 921,600 cycles. So it's nearly 1 million instructions per second. In the other word, we can say that 8051 can execute nearly 1 million instructions per second. That is quite fast. Okay, just now we calculate that in 1 second, uh, just now we calculate that 11.0592 can generate nearly 1 million instructions per second. So 1 second it can execute nearly 1 million instructions. Okay, now how can we use previous information if we want to calculate a specific type of instruction? Again, we assume that the crystal is 11.0592, and we know that 12 pulses is for one machine cycle. So 11,059,200 pulses is for 1 second. Okay, we have previous one. Okay, 11,059,200 is for 1 second. So for 12 pulses is actually, we just divided it by 11,059,200 pulses, and for 1 cycle it's also equivalent for 1 cycle, because 12 pulse is equivalent to 1 cycle. So therefore we've got a T instruction. So T instruction is time to execute a specific time of instruction is equivalent to number of cycles times 12, actually 12 pulses, divided by the value of the crystal frequency. Okay, now time for exercise. Okay, if we have several type of crystal oscillator, let's say we have the first one is 11.0592, second one is 16 megahertz, and the last one or the third one 20 megahertz. If we have for the first one, if we have 11.0592 megahertz, it actually can execute one machine cycle. It can execute 1.085 microsecond for 1 cycle. For oscillator with a 16 megahertz value, we just divided it by the number of pulses. We've got 1.333 megahertz. So the time required is 1 over t is 1 over 1.333 megahertz is equal to 0.75 microsecond. And the third one, we have the oscillator is 20 megahertz. 20 divided by 12, we've got 1.66 megahertz. So for one machine cycle can execute 0.6 microsecond. It's pretty fast, isn't it? Okay, now we look on the specific instruction for a 8051 system that utilize 11.0592 megahertz. Find how long it takes to execute each of the following instruction. Okay, we have A, move 55 decimal value into register up 3. Then B, we have decrement the value of up 3. And C, we have decrement jump if not 0, the target, and R2. And then we have LJMP or long jump. We have SJMP or short jump. We have NOP, no operation. And we have mul AB or multiply A and B. Okay, let's have a look. Okay, I bet you have to do it yourself, this one. It's quite straightforward. Okay, some simple exercise. Assume we have a 16 megahertz crystal frequency. Find time to execute at R1 into A. So basically we have same instruction at R1A. We just replace the crystal frequency value. So please look on the 8051 instruction list and find the number of cycle for add instruction. Just multiply the number of cycle with 12 and divide it by the crystal value. So we've got the time to execute add instruction. Okay. On the more realistic assembly code where we have used previously. Okay, example 1. Find the time taken to execute the following program if the crystal frequency is 11.0593 megahertz. Okay, what this question required is we want to the question asks us to calculate this portion of the assembly code, how much time delay generated here if the crystal frequency is 11.0593. So we have moved 200 decimal value into register R3, DJ and Z, here R3, and then return. What does this line do is move 200 decimal value into R3 is copy the value of 200 decimal into R3. Now R3 or register R3, the value inside register R3 is now 200. DJ and Z, here R3, what does it do is decrement the value of register R3, and if it is not 0, it will go to the label which is here. So for example, now register R3 is 200, and then it checks the value of R3 and decrement the value of R3 from 200. It will minus 1, it become 199. 199 is not 0, so it will jump where it should jump. It should jump here. So where is here? Here is here. So it will do this line 200 times, because from 200 it will minus 1 become 199. 199 minus 1 is become 198, and it actually doing the decrement is 200 times. And when it's achieved, and when the value of register R3 becomes 0, you will go to next line, which is red, or return. So where it should return, it will return to the next main line, or the next main program, which is CPLA. Okay, now we just want to focus on how long the time delay generated in this subroutine. Okay, look on the 8051 instruction list. We've got move instruction. Move instruction is actually one machine cycle. DJ and Z, we have 2 machine cycle, and RET we have 2 machine cycle. So using the formula straight away, we have 1 machine cycle times by 12 divided by 11.0592. It doesn't make any difference. It doesn't make many difference between 0592 and 0593. So we have the first line, it will execute 1.085 microsecond. For the second line, it is 2 machine cycle, DJ and Z. Please refer on the 8051 instruction list. We have 2 machine cycle times by 12 divided by 11.0592, and because of this line is executed 200 times, so we divide it by we multiply it by 200. We've got Okay, now let's look on these examples, or this exercise. Find the time taken to execute the following program if the crystal frequency is 11.0593 megahertz. Okay, the first line is delay. Delay is just a label. So move 200 decimal value into register R2, and then move 250 into R3. No operation, no operation. DJ and Z here R3, then DJ and Z again R2, and then return. Okay. If you observe here, we have two DJ and Z, where the first DJ and Z will go to here. It's actually this one, and the second DJ and Z will go to again, which is this one. It is a little bit tricky, whereby the first DJ and Z is actually belong to these three lines, where we can call these three lines is the inner loop, and the second DJ and Z go to again, which is this one. So again is actually the outer loop. Okay, on the first line, the value of register R2 is 200 decimal, and the value of register R3 is 250 decimal. Just copy the value of 200 decimal into R2 and 200 decimal value into R3, and now R2 becomes 200, or the value of R2, or the value inside R2 is 200, and the value inside R3 is 250. Please also observe that I put the amount of the machine cycle required for each instruction, or for each line. DJ and Z, as we have discussed before, is actually decrement and jump to label if not equal to 0. So here we will decrement the value inside R3, and if it is not 0, it will go to here. Where is here? It's actually this one. So so it will decrement the value of corresponding register, which now is R3, and jump to label if it is not to 0. So it will jump to here. Okay. I've changed the color that for inner loop is red and for the outer loop is blue, in order for you to have a better visualization. Okay, from this line, or from inner loop, we can see that the inner loop will decrement 250 times. Why? Because of the value of R3 and the instruction of DJ and Z. Okay, instruction of DJ and Z. So it will keep doing this instruction, or these three lines, 250 times. So it will decrease the value of R3 for 250 times before it becomes 0. If it then, when R3 becomes 0, it will go straight to the next line, which is DJ and Z R2 again. Okay, now when it execute, when the pointer execute, when the program execute DJ and Z again R2, it will execute the outer loop, whereby the outer loop is repeat itself for 200 times because of the value of R2 and the execution of DJ and Z instruction. However, please observe that every time R2 is decreased, it will go to again, and it will go to again, whereby it will again copy the value of 250 into R3. Then it will execute the next line, which is no operation, and this line will decrease again the value of R3. So in the other word, at the same time the outer loop is executed, the inner loop will also repeat the decrement for R3, for 250 times. More precisely, the execution of inner loop will repeat 200 times on top of 200 times of the outer loop. Okay, now it's time to calculate. Um, for inner loop, we have because of the crystal frequency or is 11.0592, we have for one machine cycle we have 1.085 microsecond. So, and then because of these instruction will repeat itself 250 times, we multiply it by 250 and just observe that the mission cycle is 211, 211, so the total is 4, so 1.085 microsecond multiplied by 250 times of the repetition and then multiply by 4. We have 1085 microsecond to only to execute the inner loop. So for the outer loop, because of the inner loop will also repeat itself 250 times of the outer loop, so we just multiply by 200 because R2 or the decrement of R2 is 200 times because inner loop is inside the outer loop. So we just multiply 1085 microsecond multiplied by 200 because of 200 times the value of R2. So we have 270,000 microsecond. So this is what we have because the inner loop is a repeat 250 times itself, but on top of that it will also repeat 200 times. Okay, now it's time to calculate the outer loop. Because of the outer loop only repeat itself 200 times, and we have this line dj and z again R2 and move 250 into R3. These two, the total up of the mission cycle is 3, so we have 1.085 microsecond times 200 because of 200 is 1 because of the decrement of R2 and multiply by 3. This is the total of the mission cycle of the outer loop. So we have 651 microsecond. Finally, for the very first and last instruction, we have move 200 R2, we have 1 mission cycle, and RET, we have 2 mission cycle. We multiply it by 1.085 microsecond. We have 3.255. So just total up everything. So we have in total we have 217,654.255 microsecond or 217.654 millisecond to execute the program or to execute the code, to execute this code. Okay, thank you very much. I will also give you some exercise. You can refer it in our Unically e-learn. Please, I will consider it as an assignment. Please submit on time, and thank you very much for listening my video. Thank you very much.